The third method that we're looking at in order to calculate the dynamics equations of motion is Lagrange II. So this is an energy-based method which will in the end result into something very similar to what we have seen previously. Now Lagrange II works the following way. You first determine the Lagrangian, which is nothing else than kinetic energy minus potential energy. And the Lagrangian equation says that we can take the time derivative of the partial derivative of the Lagrangian with respect to generalized velocities minus the partial derivative of the Lagrangian with respect to generalized coordinates equals to tau. So the external torques or the actuation torques of our system. Now we can additionally include the following dependencies. We know that the potential energy, U, is only a function of configuration, never depends on velocity, while the kinetic energy depends both on the configuration as well as on the velocity. So that means the partial derivative of U with respect to Q dot equals to 0. So this simplifies then to time derivative of the partial derivative of kinetic energy with respect to generalized velocities minus partial derivative of kinetic energy with respect to configuration plus partial derivative of potential energy with respect to configuration equals to torque. And we have multiple components that we see in here. First part is all the inertial forces, so mass times acceleration plus Coriolis part, and then we have the gravitational part, which is essentially the contribution that comes in through this potential energy equals to external torques. So let's have a look at kinetic energy first. If we define the kinetic energy in joint space, all we need to do is we have to take 1/2 q dot transposed m q dot. So that's nothing else than 1/2 m velocity squared if we write this in a linear form, but this here is in matrix form. We can also look at the kinetic energy for all the bodies, which we know it's nothing else than the linear energy that we have there, which is the mass of the body times the velocity squared of the body at the center of gravity. And then we have the rotational energy of a rotating body, which is nothing else than inertial tensor in the middle, pre-multiplied and post-multiplied with omega transposed and omega. So this is the rotational energy of a body, and this is the linear energy of a one body, and I have to sum it up over all the existing bodies. Now we can again include the kinematic relationships, which says that velocity of my center of gravity of body E is Jacobian at that position times the linear times the generalized velocity. So it's the Jacobi, which is again mapping joint space, generalized space to task space or end effector space, or in that case like center of gravity velocity, and the same also for rotational direction. With this together, what we get is kinetic energy is 1/2, and then we include here for this r dot in this formula, we include the relationship between Jacobi and q dot. So we have here that part, and we have the same for the omega in here. So we have the linear part and rotation part, and since we can bring out the q's here, and we know from the formula up here that we have kinetic energy equal to 1/2 q dot transposed m q dot, we can simply see here in the middle the mass matrix. Now this is the formula that we've seen already in the projected Newton-Euler, so that shows you that this Lagrange II, projected Newton-Euler method, they're more or less one and the same. There's slightly different derivations, there's slightly different pros and cons, slightly different ways of how you do the calculations, but in the end it doesn't really matter. It's like ending up in the same equations of motion, and for all of that what you need is nothing else than a couple of Jacobians and a couple of masses in inertia tensors. It's also very similar for potential energy. There's in essence two sources for potential energy. One is gravitational forces. So we know that gravitational force is the mass. It's g, so I put it here g not as a vector but as a scalar value, and then you have the direction where g acts, which means I can then write my potential energy to be nothing else than these gravitational forces times the motion we're doing in linear direction. We have to do this for all the bodies. So the higher up we are, the heavier we are, the more potential energy the system has. The second source of potential energy is are springs. For springs, we know how to calculate the energy. We have the force, which is depending on the spring constant and its offset, and then we have the direction of it. And then if you want to calculate the potential energy, all we need to know is 1/2 k times displacement squared, and that gives you the total energy, the total potential energy, which you can then use in the Lagrange method. And to conclude this video segment, we're gonna go again to this simple example of the cart pole pendulum. So the cart that can move in linear direction and the pendulum that is attached to it. But now we are figuring out the equations of motion using the method of Lagrange II. That means, as a first step, we figure out the kinematics for this cart pole pendulum. We have again these two generalized coordinates, x and phi. We then define kinetic and potential energy as a function of these generalized coordinates, and then apply the Lagrangian method to end up with the equations of motion.